scanning near-field optical microscopy, software transfer and scattering, and the method which is based on both of them, tipping transfer and scattering, and after that to present you some ideas how we can use functionalizing tips in scanning probe microscopy. So let's maybe we can make some analogy with mankind with small kids. We always were interested what happened in the small scale, smaller and smaller, what pushes our world behind and so on. And maybe because the vision is the main part of our perception, it is the reason that optical microscopy plays so big role among all other physical methods of investigation, in spite of its more qualitative than quantitative methods of investigation. So in this way, after invention of microscope by Levitin, it was remarkably fast found that we have some restriction. We cannot look further and further in the micro world, and there is a thing which is called diffraction limit, and we cannot resolve smaller details of our object than this diffraction limit, which is approximately half of the wavelength. So people continue to look for some methods how to overcome this limit, and at the moment there are not one way to do it, but maybe the near-field optical microscopy is the most universal way how to overcome the diffraction limit. In fact, it's interesting to note that near-field optical microscopy had a chance to be realized in 30s of last century, much earlier than other scanning probe methods, because the first article on this topic was published by Sinch in 1928. In this article, he completely described the construction of the near-field optical microscope, but the feedback loop, he didn't think about the necessary of the feedback at that moment, but he completely described the whole construction and even proposed mechanical screws to drive all elements of this device. He understood that these screws has to be precise enough to make nanometer movement, and he found the mechanical company which promised to produce screws like micrometer screws, but with necessary precision. But probably later he realized that it's not a good idea to use mechanics in this case, and his third article, it was published in 4 years later, in 32nd, he proposed piezoelectric drivers, what is the base of all modern scanning probe microscopes. Unfortunately, his disease stopped his investigations, but in this article he wrote that the idea of this method was given to him by one outstanding physicist, and just now it was found that he lettered with Einstein, and he proposed to Einstein his idea how to do it, but maybe Einstein decided that it's a very brave, very crazy idea, and he proposed another way, which was published in this article. In fact, this idea is really rather simple, and after that it was rediscovered, at least 65. He considered the resolution of light microscope, but in Fourier space, and the first experiment was made in 70 seconds. But in this case, the experiment was made with a wavelength of 3 centimeters, and immediately demonstrated the resolution lambda over 60. The idea is really very robust, and mankind used it for a long time. So trying to look through a small hole and to find something interesting. But in fact, when the people finally realized this method, they found the whole new world. So the idea, which was published, may be roughly described in the next way. If we take absolutely opaque screen and make a very small sub-diffraction hole there and put it directly on our object, we have to see nothing but only the area opened by the screw. Another question, whether we see anything through such small hole, but as you saw in the experiment, it's 3 centimeters demonstrated that it's possible, and all other history demonstrated it's a normal way. In fact, what we have after this small aperture, it's some spreading of our electromagnetic field, but it's not instant process. So we don't have the field everywhere in this half space immediately after the aperture. So there is some analogy of electromagnetic field with viscous media, and we can consider that we have some spreading of our beam after that, and only on the distance which is comparable with the wavelength, this field is spread over the area of comparable with the wavelength. But just after the aperture, we have much more squeezed field, and just this field will interact with our object, and we will receive the information, if we can register it, just from the area of interaction of field with the object, which is defined by the size of the field localization. So it's such a rough description of the background of near-field optics. And in fact, after that, there were few groups who worked in this direction, and they received the results which are considered as the beginning of near-field optical microscopy. It is a group of Dieter Bohl, who worked in the same laboratory where 2 years before scanning tunneling microscope was built. And on the base of that device, already in '84, he published the first, he built the optical near-field microscope, and 2 years later, publication about scanning tunneling microscope, he published the first results of near-field optics. Few scans which he made. It's interesting, he titled his article as Optical Stethoscopy, because at that time he realized that this approach was used for centuries by physicians, because with the help of stethoscope, which has the size of centimeters, they define the position, for example, our heart or some inflammation in our body, also with precision of centimeters, but they use acoustical waves with the wavelengths of meters. So the second group was the group of Aaron Lewis in USA. In fact, he didn't make the microscope, and at that time he only demonstrated that we really can see the signal after such subdiffraction. But it's interesting that there was a third group, the group in Göttingen, where Ulrich Fischer at the same time received also few scans. He didn't build the completed device, but he received few scans, and as Aaron Lewis in '83 year, he presented his results at other conference in Germany. But ironically, if proceedings of that conference were published in '84, and Aaron Lewis is considered as the father of near-field microscopy together with Dieter Bohl, proceedings of that German conference were published 7 years later. So at that time, near-field microscopy was already well developed, and nobody paid attention for that publication. In fact, it was only noticed also for that year in annual report of German Optical Society, but Ulrich Fischer is not considered, at least in the wide area of physicists, like another father of near-field optical microscopy. But he made many other contributions to this field. In fact, there were many results obtained in the first years, and here are a few of them, which are received by Betzig. He started from the group of Aaron Lewis. It's a different kind of optical contrast, from polarization, from other things. He made the first experiments with a single molecule and many others, but I will not show all examples because there are many of them and my time is restricted. So I only want to demonstrate you this article. It is 2 years later, a few years later, it's a Fisher et al. Its article is remarkable for a few reasons. It is the first investigation of the plasma by near-field optics. In fact, just now, it's maybe considered like a marriage of plasmonics and near-field optics, those fields which just now considered like undistinguished in this nano-optics. Additionally, it's the first realization of apertureless structure. It's also a very interesting realization, but I will say about later. And it is the realization of the pristine idea of Sinch, because he proposed to use not the aperture, he proposed to use a small spectrum. But maybe this idea was too crazy at this moment. So here, results were obtained with a small scale. So, to consider what is the physical background of this method, surely we can consider something like an analog of Young experiment with two slits. And in this case, if we make slits very small with some diffraction size, and separation of them also smaller than the wavelength, if we use the configuration of the standard experiment, we will see only one. So we cannot resolve this signals. But if we take, like, for our registration, the third slit, also sub-diffraction size, and we'll scan the slit along of our object, so you may see, depending on the distance between these two screens, we can obtain better and better resolution of signals from these two previous ones. So in reality, field is localized after this diaphragm, after this aperture, and it is registered by our third aperture. It may be calculated directly by a bit cumbersome, but very straightforward integration, but it is, in fact, it's not yet explanation of the physical background, it's only expressions. And to understand the physical background, we have to consider what is, in reality, the diffraction limit. It was found by Aber that if we use the standard optics, diffraction pattern of our pupil consists of few right rings, and the central ring is so-called Aber ring, is limited in size by this expression, and we cannot focus our light tighter than this central ring. So it was proposed so-called relay resolution criterion that if maximum of the second such picture coincide with the minimum of this one, we can resolve these two spots. But in fact, this thing is based on one fundamental physical principle. It's the Heisenberg uncertainty principle, which, you know, we cannot define position and the pulse of our object more precise than some limit. So if we use another quantum mechanical expression which connected the wave vector with the pulse of our object, we will immediately receive the similar restriction for determination of the wave vector and the position. So what we do when we want to see our object of some restricted size, we shine light with a photon which has a wave vector and frequency. Surely by geometry we have projection of this wave vector, but if we want to know that we investigate just this object, we have to be sure that our photon interacted with it, so our photon was restricted in the size of this object. Correspondingly, scattered photon has some change of wave vector in this plane, and we have two in other components. Surely there is a standard equation which connects the total wave vector of our photon with two components, and if this horizontal component became bigger than our k, it means that perpendicular component became imaginary, so the field became evanescent. We cannot accept this photon anymore by the standard optics, because it doesn't propagate to our direction. So if we consider the situation when all photons will be transferred, definitely will be transferred to evanescent photons, it means that it's limited by this expression. So if we want that at least one photon come back to us, we will see that the size of the object is restricted by the half of the wavelength. Surely, if we restrict our optics by some angle, numerical aperture, we will add just the cosine, which is in the denominator before. So, in fact, diffraction limit means that by standard optics, we cannot accept propagating photons. But it's not the restriction for obtaining information by optics from the objects with the size smaller than the half of the wavelength. The only notice that information will be hidden not in the propagating photon, but in evanescent wave, which doesn't come to our detector in standard wave. And it was the reason that for a short period, for example, near-field optics was called the optics of evanescent waves. So in fact, what is evanescent wave? It is the standard description of our wave, but one component of the wave vector is imaginary, so we can rewrite it in this expression. This is the wave which propagates, for example, along some plane, but decay perpendicular to this plane. It is a field from the surface plasma. It is the field which exists in total internal reflection. It is also the part of the field of the standard dipole field. We have propagating component, which is proportional to 1 over r, and we have fast decaying components, which doesn't come to our detector. It is just the near field. So how can we register it? Also, either we make our waves have leaky wave modes. It's the standard geometry for surface plasma excitation. It's what is called forbidden light, and we can see it with immersion optics, but also we can use optical reciprocity. So if you take our small object and shine light on it, the information about the size of this object, if it's subdiffraction, will be hidden in decaying near field. But if we take the second object with a similar size and put it into the area of localization of our decaying field, this object will correspondingly, like reciprocity, will transfer this decaying near field to propagating one, and we can register it. So, in fact, such idea we used it before, like blade excitation of surface plasmons. Excitation is by roughness, interaction of molecules with the surface, where waves in the substrate were created by the dipole just on the top of this. So, it is just the physical description of the processes which we have in near-field optical microscope. So we have information about our subdiffraction details in evanescent waves, and to restore it, we take another subdiffraction object and put it into the area of localization of this field. So in such a way, we receive the normal optical signal about the subdiffraction elements. But this consideration shows a very important feature of near-field optical microscopy. In fact, this method doesn't have what is called passive tip. So there are approaches which are called photon scanning tunneling microscopy, where people claim that tip is rather passive in this case, but it's passive from the point of view that it doesn't disturb very much the distribution of the evanescent field of our internal object. But it cannot be passive in the image production. Because in the production of image which we observe in the microscope, our tip plays absolutely the same role as our object. It cannot be passive in principle. It is maybe the reason that so many different investigations cannot be compared directly, because people use different tips. More or less, they have common features, but in details they are different, and we will receive probably different a bit different pictures using different tips. So the tips itself may be roughly separated into parts. It's the tip which was used since beginning. It's the aperture tip, where it is a fiber which was produced basically pushed near field optical microscopy very much, because before the construction of the tip was a piece of art, practically. But he proposed to use tapered optical fiber, tapered pipettes, covered by the metal, with a small aperture in the bottom. So the light shining through this fiber will comes out from the aperture and shine light on our object. Another class of tips, so-called apertureless tips, where the light comes from outside and the scattering on the tiny apex of this tip will create the necessary evanescent wave in this case. Surely, even these two variants, together with optics, give us a variety of possible configuration of this device. We can shine light from outside, through our object, through the fiber, if it's possible. We can register reflected signal, transmitted signal which comes through the fiber. We can excite our system with a total reflection. We can register what is called forbidden light in this case. So, all variety of any optical configuration. But there is the tip which doesn't come to this rough scheme. It's a tetrahedral tip which proposed by Ulrich Fischer. It is a very simple construction which you can make in few hours. It's not one. It is a fragment of the cover slide. It's made by the method which was used for a long time and is used now to produce glass knives in electron microscopy. Because if we break our glass, this edge of the break is very sharp. So if we make it twice, it will produce this corner. The radius of the curvature of this corner is about 5–10 nanometers. So after that, it's covered by the metal, which producing of this edge. You may see this is electron microscopy picture of this tip. And when we shine light through this tip, it has no aperture here, but we shine light through the tip, and by sequential dimension of plasmonic and electromagnetic modes in this construction, finally we excite the dipole mode at the apex, and it is really bright source for near-field optics. And you may see we have advantages of the asymmetry of this object, because if we excite circular aperture or circular particle, we have two lobes where our field is localized. If we excite triangular object, we have only one lobe with the field localization. So we immediately have improvement of the resolution. You may see this is calculations, this is experimental results. And I want to separate two situations. Situation which I call modified tips, where we make something with our tips, but only to improve its own properties. So, for example, to improve the brightness, put in the nanocrystal of luminescent nanocrystal, naftacen was used here, or for example, attachment of small additional particle to increase the localization of fields in this case. But all these approaches were done only to improve brightness or resolution. Further steps in this direction, it's producing tips, nano-antennas. For example, to remove such a finger here and the appropriate lens, you may see much brighter and more localized field. In this case, this is a standard aperture, this is the aperture with this finger. Further, even construction of more sophisticated antennas, like bow tie antenna here, or tapered construction of few nanospheres, everything for better field localization. But I will distinguish Another case is functional isotopes, where the reason of our change of the tip is not only to improve its properties, or even not to improve its properties, but to make it sensitive to some other things. And in this case, if we put something on our tip, we can follow the change of the properties just of this object. And it will give us information about the nearest environment of our tip. So it was in such a way this idea was proposed by my friend Igor Yurchenko on the basis of investigation of proximity dependence of optical properties of fullerene. And in such a way it was used in the first by Sikatsky, who used this similar tip like Kopperman before, but not to improve the brightness, but to use the first energy transfer between molecules deposited on the tip and on our surface. In this case, it's not only improves the resolution because the range of energy transfer in this case is very small, it's something like 10 nanometer, but it also immediately separates the wavelengths of our registered signal from this, our excitation. In fact, there are not so many approaches in this direction, and maybe more obvious thing was realized only a few years ago. In this case, luminescent crystal was deposited on the tip, and the scanning of plasmonic structure revealed the field distribution on this structure by the intensity of luminescent signal. But in fact, what is the problem in this case? It is the use of luminescence, like in the first transfer, like here. The second, to prevent immediate bleaching of our object. All of them were deposited in crystal or in the film with these sensitizing molecules. So it is the object of not molecular size. So our resolution is limited at least by the size of this nanocrystal. Surely the near-field optics is not the ideal method. There are many drawbacks in this way. For example, it's a very small intensity which comes out of the tiny aperture. It's proportional to the force power of the diameter. So it drops down very quickly. Moreover, we have the area of evanescent field here, so not all light comes to our aperture. It's a very difficult interpretation of this result, because the field is described by this Lippmann-Schwinger expression, and the result is a practically coincident picture in the case of topographic defects or some optical contrast in our sample. So it's very difficult to distinguish, for example, what is the reason of the change of registered field. Because it's the field which we register, it's very much integrated according to this expression. There are other things, and it was realized 10-15 years after the first experiments in near-field optical microscopy, that it is not the microscopy like we expect. Because in the standard microscopy, the picture which we see is constructed by reflected and transmitted waves. In this case, we have only scattering. For example, could you say what is this picture? You may see only the repeated construction of combination of dark and bright spots, but it's difficult to say that it is projection pattern. It is gold triangles on the surface. Here, another example, like I said before, it's a difficulty in the interpretation. What was the reason of the change of the contrast? Because what we can measure is practically only the change of the contrast. So one of these samples is initial gold layer, the second is a gold layer is covered by molecules. But to be honest, I forget which one is clear here. So, it would be good to change the wavelengths to avoid this interference of our exciting wavelengths with the scattered one. But in this way, if you want to reduce the fluorescence, you immediately stuck to the problem of bleaching and photodestruction. Because field intensity is rather high in the area of localization, and the processes of bleaching is very fast in this case. But there is another optical process which is not resonant and doesn't suffer from this, at least it may be not resonant. It's the Raman scattering. So what is it? If we have our object and we illuminate it by external light, we create the dipole moment of this object, and this dipole moment oscillates with the frequency of our excited light. So correspondingly, it scatters the light with the same frequency. But if this object has own oscillations and its polarizability of dipole moment is described by this expression, we will immediately have that the scattered signal will have not only the central component, but also shifted components, so-called stocks and anti-stocks scattered light. Or, speaking of the language of the second order quantization, we can say that our initial photon create excitation of our system. This is Stokes mode, where the scattered frequency is lower than exciting one, or anti-Stokes mode, photon absorbs some excitation of our system, and scattered photon has higher frequency. The only problem in this case is that the cross-section of this process is much smaller than the cross-section of the fluorescence. You may see giant gap of the intensities. So it was a problem for registration of small amounts of material. In spite of its very good method, it gives us exact fingerprint of compound we have in investigation. But after that, the new era of Raman scattering started after the experiment in 94, where the Raman spectra of pyridine was detected from layer absorbed on the silver electrode. But in reality, the era started 3 years later after repetition of this result by 2 groups, and after that, the number of articles on SERS was rising like avalanche. So there are 2 reasons which are distinguished like a reason of enhancement of the signal. It's a chemical one, interaction of adsorbed molecules with the substrate, but I'm interested for my topic just in electromagnetic one. So if we have our small particle, like Dolgov shown yesterday, its polarizability of this particle, its in me description is defined by this expression, and if our denominator is in resonance, we immediately have what is called dipole resonance of this particle. So if we approach this condition, we have excitation of the resonance, but we have no divergence in this case, and we can define that the highest enhancement of the intensity on the surface of this particle is described by this expression. It is restricted by the damping, so imaginary part of the dielectric function of our material. And you may see that biggest enhancement we can expect for silver, where the damping is low, it's something like a few hundreds. But for the gold, it's only 2 is half. It's just because of higher damping of gold. But we can improve this situation if we take not round particle, but the elongated one. In this case, we have what is called a depolarizing factor, and this depolarizing factor arises here. And if we have this ellipsoid with the eccentricity of about 3, it means that the polarizing factor is only 1/10. We immediately receive that we can increase the intensity near this edge of our particle almost in 5 orders of magnitude in the case of silver. So it what is called lightning rod effect. But, well, it's plasmonic enhancement and lightning rod enhancement are considered like different things, but in fact, it is a lightning rod enhancement of the plasmonic field in this case. So, in fact, they are not so much separated. But at least it demonstrates that we can expect very strong enhancement of our signal for specific substrate or specific particles which are used in our experiment. It's another consideration. If we take two particles, we can analytically describe the polarizability of this situation, and we can obtain what is called, in this case, configurational resonance. So at corresponding distance between these two particles, we will have also a very strong field enhancement between us. So it was the background of proposed concept of hot spots, and it was claimed that we can register Raman scattering from one molecule if it's corresponds in appropriate position in this hot spot. Just now there is some reversed movement. For example, one dyne claims that just lightning rod effect is enough for one molecule SERS because the spectral range of excitation of enhancement of both incident and scattered field is maybe rather wide, and the spectral range of this resonance is more narrow, so it's not enough to enhance correspondingly both incident and scattered light, but it's not so important at the moment. There are another construction, so-called tapered construction. It may be made from few spheres with decreased size. It may be the cone where plasma propagating along this cone has adiabatic focusing, and we have yield enhancement of the field at the apex. So it was explanation in the rhythm of SERS, and I want to demonstrate only one example, maybe not only as SERS. It's a fantastic idea of Elio Fabrizio, and he made it to register, to make a sensor for very small amount of material on the base of SERS, because as I said before, we can register, and it was made and demonstrated, SERS signal from one molecule. But in this case, we have to put our molecule just at this position, or just at the tip of our structure. And if we have very diluted solution with our molecules, we have to wait until diffusion will put our molecule in the corresponding position. If we decrease, for example, it's to hundreds of atom models, this solution we have to wait for years until our molecule will come in the appropriate position. So what he proposed is to make such an absolute hydrophobic surface, which is constructed from a number of pillars, and each pillar has very sharp tip on the top. This pillar is excited by external light, and through this grating, which is made on this tip, its surface plasma is enhanced. It is enough to register the SERS signal just from the apex of this tip. Because this surface is absolutely hydrophobic, practically absolutely, you may see that he deposited the drop of analyte on the top. This is the size of this drop at the beginning. And during the evaporation of the solvent, these drops doesn't spread on all this area, but it shrinks and jumps from one pillar to another until it's already not solution. And only in this last final step, it will leave the material which is dissolved there in such an area. You may see that the rest of this drop, with only 20 attomolar of rhodamine, was left only on 3 pillars. And you may see exact Raman signal from each of these pillars. And the spectrum gives you the fingerprint of the Raman. But if we consider, as you saw, the structure for SERS, it very much resembles the tip which is used in near-field optics. And it was the background of the idea proposed only 1 year after the creation of near-field optics, that if we take small nanoparticle and we'll scan it along the surface, we can create strong enough field enhancement just between the particle and the surface, and we can measure SERS signal locally from this area. Surely TIBS is not the separated particle. It's only the example how to realize just this idea, for example. It is a particle which is attached on the glass fiber, and this structure is immersed in the index match liquid. So in scattering, we see no glass fiber. We see only scattering from this attached particle. But it may be some trick. It's not necessary in reality for TERS experiments. And in this direction, there was a long time, about 10 years, of registration of SERS, standard SERS, with help of additional tip. So during the modulation, it was said that we register SERS signal, but from the rather small area. But real TERS experiments were made almost immediately at the same time in few groups. So as before, few groups came to the result neck to neck. And the first experiment is considered like experiment made by Volker Deckert, but similar results obtained at Anderson and Satoshi Kawada. So what we have in near-field optics? We have all necessary enhancement mechanisms. We have localized plasma here. We have light and rod effect due to the shape of our tip. We have additionally gap mode enhancement due to the interaction between tip and substrate. We can consider it's like interaction of the dipole, which is localized here, with the dipole, image dipole in the substrate. So it's corresponding to the situation of two interacting particles. The field between them is enhanced. And you may see calculations of the field in such a structure. It is dependence on the distance between the tip and the surface. It is a shift of this resonance, which is called in this case gap mode. And it is a shift just well described by the chain interaction of the dipole localized here with its image. So it is a field enhancement just in this region. We can rather easily describe it in the model of interacting dipoles, and it will demonstrate that this strongly depends also on parameters of our substrate. So we have many possibilities to play with parameters of our system to receive a TERS signal. And you may see at the moment there is absolutely incredible results. It is a results published last summer, where there was TERS was made with sub-nanometer resolution. Because in addition to high resolution of near-field optics, here we have non-linear field enhancement, so we have additional field localization, and this is a porphyrin molecules with the size of few nanometers, and you may see the picture of this molecule made with different Raman modes of this molecule. This is the theoretical calculations of this molecule, this is the experimental ones. So, at least I described to you the background of this method, and just now I want to continue, but before, surely it's also not ideal method. At the moment there are many problems in realization. Maybe the main is the reproducibility of the tip, because in this case our results even strongly depend on the shape of our tip than in near-field optics. It's a problem with the tip contamination, it's a gradient field effect, which is very strong in this case, it's a cross-polarization just near our thing. But it is used, and other interesting results are obtained in this way. And we also worked in this direction. And in this way we proposed the concept of Raman probe for near-field optics. Surely we realized that well, it was after our first experiment, that we are in favorable situation with tetrahedral tip, because standard problems of TERS is that our focused external light has a very big spot in comparison with the apex of our structure. So from all this spot, we can expect SERS signal, we can expect photo-bleaching, photo-degradation of our object without making any measurements. So we spoil our sample in much bigger area than we investigate at the moment. Any attempt to use a standard tip were bad because such tip with aperture, which more correspond to magnetic dipole than to electric dipole. The use of attached nanoparticle, maybe that time it was not successful preparation, because more modern tips should work better. But in that case, it fallen down, so results were negative. But what we had with our tetrahedral tip is had no aperture, but use the plasmonic mode there. That we have the light which excites the plasma, which is inclined according to our substrate. So we can satisfy all necessary selection rules in this case. We have no external illumination, no bleaching of our sample, and so on. After that, such a construction was proposed by Rashke, something like 10 or 15 years after creation of tetrahedral tip, just to prevent external illumination of our object. It is a construction which I shown you in the sample of Fabrizio, where we excite the plasma by grating, and it propagates a few microns along the tapered structure and creates the bright spot here. It's another construction of Fabrizio, where he harvested light from the big spot by photonic crystal, and after that it's focused on this. So these structures may be better, the cost of the preparation of such a structure with tetrahedral tip is comparable. So we immediately received that with tetrahedral tip we have very good results. It's a spectrum of thiophenol, stains all, molecular green, and those red are spectra with retracted tip. But we found another thing. So you may see here, it is a spectra with contact tip for molecular green and stains all, and these are spectra with retracted tip. But these materials are only physisorbital on the surface, and after one or two contacts to our substrate, we received another spectra with retracted tip. So we can resolve all lines of Raman lines of our material, and it corresponds to published one. But we see something similar with retracted tip. And moreover, if you multiply it approximately the same coefficient, we see well coincidence of this spectra with the TERS spectra. So in fact, in this case, molecules were connected to the surface rather weakly, and tip picks it up during the contact. Because during the STM contact in ambient, practically every time we have creation of a water breach from the condensation moisture from the atmosphere. And in this water breach, we can expect migration of molecules and picking up of molecules by tip where was reported before. So what we can expect if our molecules are on the tip, or if we make intentional coverage of our tip. We can expect protection of our tip from contamination, from aging. It works, for example, for silver. It's hydrophobization. In this case, we can decrease the influence of that water breach, maybe some change of STM conditions, but not only this. So this is experiment where we intentionally covered by our tip with thiophenol. It's chemically bound to the metal tile, which is strong in Raman. And you may see, before was the spectrum of thiophenol adsorbed on the surface, but this is the spectrum adsorbed on the tip. And black one, it's the spectrum which was registered with the compact with additional enhancement by the gap mode, but red one, it's the spectrum registered without substrate. To say that we have no long range interaction, this is a spectrum with no substrate. So you may see absolutely clear Raman fingerprint of tyrphenol adsorbed on the tip. Maybe we were lucky because later it was realized that the tetrahedral tip has own modes and it has enough enhancement to give us the result. But in fact, what we proposed later, it's not dependent just on the tetrahedral tip. It's the concept of Raman probe. So we can cover our tip by Raman active molecules, and if we follow the Raman spectrum just from these molecules, we can make conclusion about the local environment of our AVAX. So we can expect that spectra would change when we scan our sample, something like that. So surely we have different tips, and we're choosing the tip with not so strong own enhancement to underline the influence of gap mode, just the interaction with the surface. And in this case, we were not able to scan our surface, but you may see when we measure spectra at different point of freshly prepared stripped of gold layer, so rather clean in first minutes, first hours, and rather flat substrate of gold layer, you may see different shape of this spectra, different inclination, existence of some details in one spectrum, the absence in other. You may see even the small shift of main lines in this case, and to prove that it's not an artifact, this few reversed centimeters shift, we made repetition in some points of our sample. You may see, again, the difference of spectra when we measured it at different points. But you may see very good coincidence of spectra when we stay at the same point. Maybe the time between the measurement of this spectra was a couple of minutes, and at one point we didn't retract the tip, so we measured it with a repetition of few minutes with a contact. And in the second case, we approached the tip, retracted it, then approached again, measured the next spectrum, retracted, and so on. You may see very well reproduction of the spectra. Moreover, they are reversible. Maybe during this time we had some shift of the intensity laser, of our exciting laser, or maybe some fluctuation of the feedback. So you may see that intensity of our spectrum was changed remarkably, but all the fine structure is reproducing. Moreover, it rised and went down. This is the number of corresponding measurements, and you may see absolutely reversible behavior of this spectrum. So it demonstrates that we have enough precision to register it. It's not the noise, and when we register few centimeters shift of the Raman line, it's not the artifact just because of interaction of our tip with the substrate. You may see this is the second one, and the fine structure of this spectrum is different. We have no explanation, maybe just the different flexibility for these rotational modes of this molecule or something like that, just the fine structure of this spectrum. It's difficult to say at the moment. The only thing we can say, we can claim that we have absolutely reproducible spectra at one point, and spectra are different between different macroscopically absolutely identical points of freshly prepared gold. So it was a demonstration that our tip covered by tyrphenol is sensitive just to the local environment. So on this base, we can propose many perspectives of use such a functional laser. For example, using the tile, which is sensitive to pH, we can register pH locally. So who knows, maybe we would be able even to monitor the work of single proton pump in the membrane. Definitely, and it seems to me it's very promising direction. We can use it in if to call it something like TERS assisted force spectroscopy measurements in IFM. In this case, Raman will give us absolutely clear indication of the connection and binding of our molecules, and also the change of the Raman during the change of our molecules. Moreover, we can use the change of the shape of molecules. We can even expect to creation such a molecular, absolute molecular rule. It maybe would be a fantastic idea, if not the talk at the same conference when it presented our concept of Raman probe. It is the talk of the Kawata group. What he used, it is a force-assisted TERS. So he pressed his molecules by the tip, and he registered the change of the TERS spectrum. And you may see here, it is the distance of the movement of the tip. So the last step, when he started to press the carbon nanotube, it's only 2 angstrom. Surely nobody knows was nanotube pressed by 2 angstrom or the fraction of angstrom, but you may see clear change of the Raman spectrum in this case. Moreover, it's interesting that tips with attached carbon nanotubes just in appropriate position, in appropriate direction, exist for more than 10 years already, and more widely used in IFM. So such tips is not fantastic. It's already made devices and may be used in this direction. And surely, if all of them are only ideas, so we can immediately try it like an internal standard for TERS. Because the TERS, as a method which uses local enhancement, suffers from unknown distribution of this local enhancement. If in TERS we integrate our signal over the surface and may more or less use averaged signal and compare different substrates, in TERS we have no idea what is the local enhancement there, and we should correspond or to use some other method to correspondingly measure this local enhancement. So we can use some reference material, but maybe the most elegant idea, as it seems to me, is just to bring this material to the point of our measurements on the tip. In this case, we are guaranteed that we have the same amount of molecules, we have constant amount of reference material, and it's deposited in the same manner on the surface of our tip, if it's chemisorbent molecules, and we can follow the Raman signal from this coverage to make some conclusions about the local enhancement. So, in this way, it was proposed by Thomas Schmidt. They used the coverage of tip to prevent it from contamination, working in liquid, and they observed the trace of ethanotile Raman line for a clean substrate. So he considered it a possibility to create such a standard, and we realized that such experiment together. Surely I will not stop here on some background, it will be the topic of my talk at the conference, but we can demonstrate that at least for flat surface we have not very big difference between the signal on the substrate and on the tip apex. Surely we have to distinguish materials we use in this case. We have to see the signal from both of them, just the opposite example. But if we do it, we can realize such a thing. You may see measurements of our deposited material. It is a distribution of our reference material, and this is the result of normalization, which is strongly different from this initial distribution. So at least we can expect that this distribution corresponds more or less just to the distribution of amount of material on the surface, in contrary to this one, where the signal is defined by the multiplication of amount of material on the unknown local enhancement. It's another example, also some difference. This is the third example. There is some correlation between this spectrum, but you may see that the strongest signal just in another point corresponds to the previous one. So, hope I demonstrated that we can realize Raman active probes for different kinds of scanning probe microscopy. We can use it like internal standard for TERS.
Два слова.
Да, я хочу change в программе сказать.
The work with my colleagues helped me financial support from different sources. So thank you for your attention. By the way, this is not arbitrary picture. This is a field distribution after such arrow-shaped aperture.
Thank you. A very nice lecture. Please, questions.
So I have a couple of questions. First question is so that what do you think in reality, for example, in our institute we have some Renishaw Raman microscope. And when we asking guys about tip enhanced Raman, they say, oh, it's not very simple because we need to give you some tip and this it will be different company and it need to adjust the position of this tip because usually we have like already optimized optical configuration and it is a question that we maybe need some long focus objective to have possibility to attach tip there and so on. And what do you think about how basically what is more suitable to buy ready tip enhanced configuration, or it's possible to modify real Raman with tip from for example from IFM and work with this? What do you think about it?
Definitely everything is possible. Moreover, Renishaw is an optical company which produces these spectrometers, but this spectrometer is a part of one spin-off company of NTMDT, which is included just in the near-field optical microscope, and it runs effective in TERS. I just worked with such a system. High Technical School in Zurich. Well, maybe I have some another comments, but in configuration with TERS enhancement, it's rather effective.
It means it's better to turn to this
NTMDT, but just now it's ISS. And few other companies. Some of them works just with Renishaw, so maybe contact them. You have just the necessary part which you connect to the Renishaw spectrometer directly.
And another small question. As far as I understood, this plasma modes, basically it's not radiative modes, as you said, like caused by evanescent field. And can you comment more, if you have these two, for example, two small particles near, how it's possible that for one particle we have evanescent mode and from second particle we obtain a radiation because of this interaction due to plasma?
It's just a reciprocal process in optics. So if you can transfer your propagating photon to evanescent one by one particle, you can use opposite process to transfer evanescent photon to radiative one, because in fact, it's like a gradient excitation of surface plasma. Your object gives you a scattering with the change of the wave vector, which is reversely proportional to the size of this object. So if you can shift your wave vector in one direction to bigger one, in the same way you can shift it to smaller one and to transfer evanescent photon to propagating.
Please, student, your questions. Student, more exciting. I know, but students at first. Yeah, all brightly. Yeah. No, it's all understand. All understand. Please, not understanding.
Thank you for very interesting lecture. You are very good lecture. So thanks. And my question is about for what it is better to use TERS, for spectroscopy or for imaging? I think for both, but maybe some preference exists.
Yes, many preferences exist only in the brain of experimentalist.
It depends.
Yeah.
It's okay.
Yeah. Once more questions? No.
Can I ask more?
Stop it. Maybe together with,
Yes.
and a little later. Thank you very much. Please.
I have
announce.
yes, small information.